I want to get into the lesson because I kind of want to walk through this and then do some practice together as a class. So possibly go through some homework questions. Right? Okay. So today we're doing cylindrical coordinates. Section 15.7. Triple integrals using cylindrical coordinates. Oh, you looked it up? Really? Oh, that's awesome. There you go. Are we all ready? Gonna get our pencils? Good idea. Oh, sorry. Okay, going back. Do you need paper? No. There's paper over there by the tissues. Do you know, it's so funny, that same stack of paper, so all I bought was just one plain little ream of paper, like 2 years ago. And I set it out there for anyone to take who needs paper, and no one ever needs paper. So it just sits there. Anyway, okay. Pencils go fast, right? Pencils disappear like lightning. Yeah. Oh, good. It's being, look at that. It's being used right now. That's so exciting. All right. Okay. Cylindrical coordinates are really just polar coordinates with a z. That's really all they are. So, cylindrical coordinates, your x is r cosine theta, your y is r sine theta, and your z is z. It's just polar with a z. So, believe it or not, it was because triple integrals were often very complicated to evaluate in rectangular coordinates that cylindrical and spherical coordinate systems were invented. Cylindrical is going to feel very comfortable because it's so similar to what you've been doing with polar. Spherical is its whole new, like, completely different thing that will be like nothing you've done before. But cylindrical is going to have, there's going to be a comfort level to what we're doing today. All right. So the only difference when you're doing a triple integral in rectangular versus when you're doing a triple integral in cylindrical is that, so your function instead of x, y, z, it's just, this is just in, r cosine theta, r sine theta, z, but you got to multiply by r. It's just like when you're doing double integrals with polar. So you have that r dr, same thing here. You have r dz dr d theta. So again, you're going to multiply by r. Q could be anything. I just use Q for the generic triple integral region thing. Ready? All right. So the first one that I want you to try, I think I might walk you through this, because I think I've been giving you guys too much to do with not quite enough guidance. So I think I'm going to walk you through this kind of slowly. We'll do this one together because I still have more after this that you guys can work on. So let's do this together as a family and see how it goes. All right, so we're going to rewrite the triple integral using cylindrical coordinates. So if you look first at your integrand, the integrand's really easy to convert, right? So your x squared plus y squared just becomes r squared, and then you put an r in front. So the only thing you have to do to convert your integrand is just rewrite it as r root 1 plus r squared, right? Okay, and you know you're going to have a dz, dr, d theta. Your z's don't have to be converted. Z stays z in cylindrical. So your z's can just stay. This, just so you know, these z's, this is a plane that's parallel to the xy plane through z equals -1. So it's 1 unit below the xy plane. And then this is another plane 2 units above the xy plane, right? So it's like a sandwich. So you have these 2 parallel planes for your z's, and then what are you doing in between? That's the stuff you really need to take a close look at, is the x's and the y's. So you don't just change the x's to r cosine thetas and be done, right? It's because you can't, like, you can't, just don't. So instead, what I would do is graph the region, and then we'll take a look and see what we've got. So this, remember, is y equals, so we have y equals negative root 8 minus x squared to y equals positive root 8 minus x squared. So remember, this is really just a semicircle. If you square both sides, you get x squared plus y squared equals 8. So when you do the plus or minus, you're just getting the whole circle. So what you have is you have a circle, and the radius is root 8 or 2 root 2. And then our x's are going from 0 to 2 root 2. So the part of the circle that we're using is that guy right there. Every time I do a problem that involves finding area, finding volume, converting limits, anytime I do any of these problems, unless it's just a problem that just says evaluate, where I don't care what the picture looks like, any other problem that has a context to it, I always draw a picture of the region that I'm integrating over. It helps me figure out what to do. So anyway, so if I'm going, y goes from negative root 8 minus x squared to positive root 8 minus x squared, x goes from 0 to 2 root 2. Okay, does everyone see why that's the semicircle? I can't tell. Yes? Looking for nods. Ryan, how are you doing? Good? Okay, Danny, don't distract Anna. Okay. All right. Okay, so now what we need to do is figure out, in terms of r and theta, what will give us the same region, right? Okay, circles are lovely when it comes to r, because you can just say r goes from 0 to whatever the radius of the circle is, right? So our r's are going to go from 0 to 2 root 2. And then to produce this semicircle, what theta values should we use? Negative pi halves to pi halves. Okay, so that's me just talking a whole bunch. Where's the answer? It's somewhere in here. There it is. Okay. So our final answer, so the integrand you just convert. The z's just stay the same. So the main focus is converting the xy into r theta. And how do you do that? For me, I need to sketch a region and take a look. Does that make sense? Okay. All right, so this one, okay. This one's fun. I gave you a picture. You're welcome. Okay. So here's what we have. We're going to find the volume of the solid region cut from a sphere by a cylinder. We kind of did this a little bit when we were talking about it. It was either this morning or yesterday. I don't remember. It might have been both. But we did it with surface area. Today we're going to do it with volume. So we're going to find the volume of this part of the sphere that's inside of this cylinder. Right? Okay, so a volume of a cylinder, but you have to know, like the top, it's not flat across, right? It's curved down and it's curved up. So you can't do the cylinder part without knowing the upper and lower boundaries, which would be the sphere. Yeah. Okay, we ready?
I have an idea. Can you just like give us the answer, and in the middle for like all the steps, we just say God exists, and then we just like write the answer down?
Yes. That's exactly what I was thinking.
Yeah, that's great.
Yes. Okay. All right. So let's take a look at this, because these should, we want to get to a point where you're like, okay, like that's my goal, is for you guys to get to a point where you look at this and you're like, all right, we can do this. We got this, right? Okay. So what do you need in order to find volume? First of all, is there one easy thing that we could do to make our lives simpler?
Yeah.
What is it? Okay, all right. So yes, that is true. We're going to convert to cylindrical. But another thing, is there something we can do to help us with symmetry? Yes, right? Okay. So since you've got this beautiful symmetry for this cylinder, top half, bottom half, you could actually just do the top half and double it, right? Technically, you could do the top quarter and quadruple it, but let's just do the top half and double it. All right. So anyway, so we're going to do, like, I don't know how to draw that. I can't draw in 3 dimensions. Okay, pretend that's like we slice the cylinder in the XY plane. That's the circle in the XY plane. So really what you're doing is finding a volume that is over this circle where the Z is bounded by the sphere. Do you want me to start you, or do you want to try it?
I don't want to try it.
You don't want to try it?
Yeah, I want to try it. So
You want to try it?
Yeah, no, the formula, please.
I'll give, all I'm going to do,
Let us try for like 5 minutes.
I'm going to let you try for 5 minutes. I am going to draw where the circle is over our like little blue man there. This is r equals 2 sine theta, so that's like your that's this circle, right? If you were to draw it in the xy or r theta plane, right? So that's x, y. Do you guys know, like, if you have 2 cosine theta, it's a circle out here. If you have 2 sine theta, it's a circle up here. Now you know. If you have number times cosine theta, it's a circle with a diameter of that number that's over to the side. And if you have number times sine theta, it's a circle with a diameter of that number that's up top here. Okay, I'm going to pause recording. All right, so your z's, first of all, the integrand. If you're just finding volume in rectangular coordinates, x, y, z, there is no integrand, because your integrals, your dz, dy, dx, those 3 integrals accommodate your 3 dimensions, and they give you the whole volume, right? So for a rectangular triple integral, if you're finding volume, there's no integrand. For a cylindrical triple integral, if you're finding volume, remember the integrand, everything has to get multiplied by r. It's like your integrand is 1, right? So now your integrand is r. So you're going to have an integrand of r. Okay. Your z's, let's do the z's first, because the z's are actually the easiest. Okay, so we have, so if we solve this for z, plus or minus the square root of 4 minus What's x squared plus y squared? R squared, right? We're just going to go from 0 to the positive z. So our z's are going to go from 0 to positive root 4 minus r squared. Is that comfortable? We all good with that? Okay. All right, so that's our z's. Now let's think about our r's and our thetas. So when I graphed the function r equals 2 sine theta, it generated this circle. Students, I encountered a number of students who were looking at that and saying, well, then do I go from 0 to 2? If I went from 0 to 2 for my r, where r was a constant of 0 to a constant of 2, it would actually produce the circle with a constant radius of 2 all the way around, right? So I don't want to go from 0 to 2. I want to go from 0 to whatever this function is. Well, what is this function? It's given to you. It's r equals 2 sine theta. So we're going from 0 to r equals 2 sine theta. Does everyone understand that? Colin, how you doing? Good? Okay. All right. Do you remember when we do polar and our function starts and ends, like I know it doesn't start and end, but let's just say starts and ends at the pole. If our function starts and ends at the pole, we got to find out what values of theta yields that, right? So you have to set your 2 sine theta equal to 0 and solve, right? Yes, yes. So you kill the 2, you get sine theta equals 0, so you get theta equals 0 and pi and 2 pi and 3 pi, and you have to pick 2 consecutive ones. So you could go 0 to pi, you go pi to 2 pi, you go 2 pi to 3 pi, right? You could go negative 3 pi to negative 2 pi, as long as they're consecutive and, and get you from pole to pole. You could split it in half again, yeah, and do, so you already have a 2 out front from splitting your z's. So since it's truly symmetrical, you could also split your theta, just 0 to pi halves and times it by another 2.
So could you double your theta, so you go 0 to 2 pi and don't times it by 2?
0 to 2 pi. Oh. Yes, you could go 0 to 2 pi and have it.
No, because you already have.
Yeah.
That's fun.
Okay. All right. So anyway. All right. So I have it here with nothing doubled. I have it here with the true negative to positive z's, 0 to 2 sine theta for your r and 0 to pi for your theta. And that would be true with nothing doubled. And then I just threw it in a calculator. To be honest, if I had to do this without a calculator, I would absolutely put a 2 in front and make this be a 0, because it's so much easier to plug in a 0. So. Okay, Zach, talk to me. Do you want to walk through it? Should we go ahead and evaluate? Because your test is no calculator.
Oh. You just
Right?
All right. Yeah.
No calculator on the test. Oh, I wrote it back. Look at that. Last year I had it wrong. So,
Not even a thought.
Symbol lab allowed on the test?
is what not allowed?
Can we use symbol lab on the test?
Symbol lab. Okay.
Can we use the periodic
Open
table?
All right. So if we put a 2 and put a 0 here. All right. The first thing we're doing is integrating with respect to z, right? So you end up with 2 integral 0 to pi, integral 0 to 2 sine theta of rz from 0 to root 4 minus r squared dr d theta. All right, so you end up with 2 integral 0 to pi, integral 0 to 2 sine theta of r root 4 minus r squared dr d theta. This actually isn't that bad, because it's just a simple use of, right? Go ahead and do it from here.
Wait, when you do use that, you have 2 Do you have to like take the second integrals?
Okay, so here, in all honesty, we did this morning before school. I did it with a few students. When I have to do U sub, sometimes I change. First of all, you're only doing it with the limits that are here. That's to answer your question, right? But personally, I find when I'm in the middle of 14 integrals and 18 variables that I don't want to have more variables, so I always just convert back and just keep the limits. I'm fine either way, right? So, but yeah, if you do change your limits to use, it would only be on that integral, not to the other one.
Wait, this is right.
Yes.
So with the 2 in the front, only count for the d theta over the dr integral.
The 2 is times the whatever.
Okay, so
But you don't, when you have, if I have 2 times A times B, it's not like that's 2 times A plus 2 or times 2 times. You don't double times it, you just one time.
So
Doesn't matter what you multiply by.
Okay.
You can put the 2 in right now if you
Yeah,
want to.
that's what I thought of, yeah.
Oh, so you accommodate your U?
Yeah.
Oh, that's kind of nice.
Yeah.
Yeah, I like that. I'm going to do that too. I am stealing your idea. Okay, so let's see. So this becomes U to the 1/2. And then 2r dr equals negative du. Oh, but we're going from something to something, and I'm not even going to write it down. From something with u's to something with u's. Okay. It actually wouldn't be that bad to just convert, but I'm not going to. So let's see. Negative 2/3 u to the 3/2. So I'm going to replace my u back right now so that I can keep my limits. So 4 minus r squared to the 3/2 from 0 to 2 sine theta d theta. Let's see. Negative 2/3 times 4 minus sine squared theta to 3/2 d theta. All right, we had almost this exact same problem this morning, just opposite. So pull out a 4. Yeah. Oh, thank you. You are so right. Okay. Minus. Plug in the 0, so you get 4 to the 3/2, which is 8. Okay. Thank you. All right. So now, putting the negative 2/3 in front. So if I pull a 4 out of both of these, so I end up with 8 times 1 minus sine squared theta to the 3/2 minus 8. Is that okay? Am I doing that too fast? I just pulled a 4 out and did 4 to the 3/2 times 1 minus sine squared to the 3/2. And 4 to the 3/2 is 8. And now I'm going to pull the 8 out front completely because I don't want to, oops, that should be this way. There. Yeah, so now I can pull an 8 out of both terms and just throw it in with the coefficient. So I have negative 16/3 integral 0 to pi. 1 minus sine squared is the same thing as what? Cosine squared. So I have cosine squared to the 3/2 which is really cosine cubed. So this is the integral of cosine cubed theta minus 1 d theta. All right, this takes us to chapter 8 from last year. We have cosine raised to an odd power.
Oh, God.
You pull one cosine out. You convert the other cosine squared to sine squareds. So you have negatives. This is why I did it with a calculator, right? Okay.
Are we gonna have any like really tricky integrals on that?
Nothing really crazy, no. So here's what you get. This becomes cosine theta times 1 minus sine squared theta minus 1 d theta. All right, so now if you let u be sine, you have to split this integral up. So let's split up the integral. So now you let u be sine. Wouldn't it feel good if we get this right? Right? After all this, right? Yeah. Let u equal sine theta. So your du is just cosine theta d theta. Okay. So you have negative 16 thirds times. All right. So this becomes 1 minus u squared du. This guy's easy. This guy's just theta from 0 to pi. All right. So now we have u, which I'm going to convert back, so to sine theta, minus 1/3 sine cubed theta, and now minus theta, all evaluated from 0 to pi. What's fun is sine of pi is 0, so you get 0 minus pi minus 0 minus 0 minus 0. So what do you end up with? 16 thirds pi. All right, I'm so curious if this is the right answer. 16 thirds. Wait, how did I get minus 64 ninths?
Oh, wait.
No. Somewhere I made a mistake with subtracting something. Oh, minus so minus pi. No. 1 minus u squared, u, negative 1/3 u cubed, sine theta minus 1/3 sine cubed, minus theta, 0, 0, pi.
I think your answer might be wrong in the actual problem.
You think so?
Yeah, because when I typed it in on SimilarWeb, it was just 65.
Whoa.
Really?
Whoa.
Really?
Yeah.
So we did it right by hand?
Yeah. So I did that already. Goofy.
Yay.
What's the answer?
I wonder how you.
I don't know. Okay. All right. I wasn't planning, honestly, on doing that gigantic problem by hand. I was really just planning on doing setup, but that's okay. All right, so let's try another one. So I gave you a picture again. You're welcome. Okay. Find the volume of the solid between the cone and the inverted paraboloid. All right? So you have a cone going up and a paraboloid coming down. They are both centered along the z-axis. And they intersect what shape?
Circle?
Yes, they would intersect at a circle, right? So notice now your xy that you're kind of finding for your what you're integrating over. This circle, it isn't on the xy plane, it's above the xy plane. That's okay. It just has to be parallel to the xy plane. So the first thing that I would like you to find is see if you can figure out the circle that these two shapes intersect at. You are not. Do you want me to show you the previous problem? Yeah. Okay. All right, I'm going back to the previous problem for just a minute. You guys, does everyone have it, the two shapes written down?
R squared. It's just 1 minus R squared equals R, right?
All right. So, Dursa, talk to me.
See, like, I think what's the answer?
So I got R squared equals R minus
R squared, what's the answer?
R squared equals R minus 1. So then this is R plus 4, R minus 3. And R equals 3.
Do you want me to take a look at your board? Here, I gotta put this, I'm gonna put the board back so that other people can work on this problem and I'll come over and take a look. Oh, here, let me pause this. So the one thing we know about where they intersect is that these are all the same, right? So if you set root x squared plus y squared equal to 12 minus x squared minus y squared, so this is the same thing as r, right? And this is 12 minus r squared. So you end up with, oh my goodness, there. So you have root r squared, or r, equals 12 minus r squared, and then you factor and you solve, and you get r equals -4 or r equals 3. So the only one that makes sense would be an r equals 3. Technically, you can have an r equals -4 going all the way around, but if you actually plug into, let's see, I'm trying to think. Let's just try. If we plug in here, if we have r equals -4, we would end up with 4 as z equals 4. And here, we would have 12 minus 16, which would be -4. It wouldn't work, right? Okay. So you just pick the positive one. All right. So our r is 3. And the nice thing is it's a circle centered at the z-axis. So r is just going to go 0 to 3. And theta is just going to go 0 to 2 pi. Now the tricky part is your z's, right? And it's really not that tricky. Oh, yeah.
Sorry, when you're setting them equal to each other, what are you finding?
So we need to find this circle where they intersect, because this circle, so quiet, guys, just so you know, whenever you're doing like an x, y, z, or an r theta, or a theta r z, these two integrals right here, those integrals, they say it contains the area of the region over which you're integrating. I like to think of it as these two integrals generate all possible ordered pairs that you're going to plug into this function. So so you got to picture, or you got to create or generate every possible combination of either x's and y's if you're rectangular, or r's and thetas if you're in polar, so that you have all the possible ordered pairs that you need to plug in order to get those z values. Does that kind of make sense? So anyway, so for this problem, the r's and the thetas were actually pretty simple. Once you solved, they were pretty simple. So r just goes 0 to 3, theta just goes 0 to 2 pi. Your z's, we're subtracting. We have an upper z, and we have a lower z. Yes, Tejesh?
Just a quick clarifying question. So
Yes.
Whenever r doesn't equal anything like 2 cosine theta or 2 sine theta, do we just assume that it's going from 0 to 2 pi?
No. You got to look at your picture and read what the question says.
But would it not be 0 to 2 pi?
What if I said, like, in the first octant only?
Oh, so only in those cases it would be like, I mean, like, because
In general, like if it's just.
I don't like making blanket statements. Like, if I don't see this, I can always put 0 to 2 pi. To me, that feels like a statement I would not want to make. You got to read the problem and do what it says.
But like,
Yes, Aubrey.
How do you know, like you said, it's centered at the origin? How do you know that?
Oh, so z equals the square root of x squared plus y squared. So one thing is I gave you the picture, right? And I do give you the picture for almost all the complicated volume shapes. So it's not going to be like it's not going to be a mystery, right? So you can see it in the picture. But to me, I know if z equals r and if z equals 12 minus r squared, oh, I know. Okay, how can I know it? Once I set these equal to each other and solve, I literally just get r equals 3. I could get some function r, like r equals with stuff, right? But I didn't. I literally just got the function r equals 3. And because of that, I know this is a circle centered well, technically centered at the z-axis. But yeah. All right. So anyway, so how do we accommodate the z's with a different function on top and the bottom? The bottom one's your lower limit. The top one's your upper limit. Right? So if you're in between two z's, it doesn't have to be that scary. Just let the bottom one be your lower limit and the top one be your upper limit. Right, I converted.
Yeah, I didn't.
Okay. Yeah, I'm sorry, I converted. The one whose function is on top. And I told you, like I said, hey, this is the cone, this is the paraboloid. Yeah. Amal, are you good?
Yeah, I just mixed the shapes.
Okay. So a paraboloid, when I see an upside down paraboloid, I think of the cone heads. I don't know if you ever saw the cone heads on Saturday Night Live, but that's what I think of. So this inverted paraboloid it's like Connie Conehead's head. And then underneath you have, which is funny because it's not a cone. This is a cone, but it's Saturday Night Live. But anyway, so the inverted paraboloid is this part, and then the cone is obviously the thing that looks like it.
They call them the inverted paraboloid.
They should have called them the inverted paraboloid heads. Yes. All right, you ready for another one?
No. Yes.
Yes?
yes.
How are you feeling about this one? You could do this. Oh, wait, that's not. Oh, that's all. Oh, that's right. That's all I had to. Wait, we're not done. We're not done. Find the part of the sphere x squared plus y squared plus z squared equals 4z that lies inside the paraboloid z equals x squared plus y squared. I'm going to go ahead and take a minute and graph this just so we can see what this looks like.
This were a problem on the test if we have a graph.
Yes. So where's my grapher? All right. So what we have is 4z equals x squared plus y squared plus z squared. Oh, look at that. Okay, so quiet please. So there's our sphere. Okay, now the paraboloid, let me add an equation. So z equals x squared plus, woo. Okay, so z equals x squared plus y squared. All right, so if you can kind of envision, we want the part of the sphere that's inside of this paraboloid. So if I could make this this sphere, like make this kind of clear, what you're going to have is you're going to have this shape that is a paraboloid for this part and then a sphere top. Okay, just kind of, except the ice cream cone wouldn't have a pointy bottom, it would have a curvy bottom. Okay, can you kind of envision that? All right, so you have this paraboloid bottom and like a slice of a sphere top. Again, what shape are they going to meet at? It's going to be a circle, right? Okay, so that's our picture. So we get this kind of a shape like that. So the first thing that we got to do is find that circle, right? Because that's going to generate all the points that we got to plug in. The z's are easy, finding the circle. So what I'm going to do personally is I'm going to do this by substitution. So I'm going to replace my z in my other equation with x squared plus y squared. And you can actually just convert right now because this is a pretty easy one to convert to polar, right? So was this a polar assignment? Was it after we learned polar? Yeah, it was, right? Yeah, okay. We're allowed to convert, right? That's all I'm saying. All right, so I have r squared plus z squared equals 4z. And here I have z equals r squared. So I'm going to replace r squared. So z squared, so r to the 4th equals 4r squared. So I have r to the 4th minus 3r squared equals 0. Fill off an r squared. So I get r equals 0 or plus or minus root 3. Which is the radius that you think will work for the circle that we have generated? I would go with positive root 3. Tell me if I make a mistake in my math. Are you guys kind of watching? You got to be watching because I mess up a lot. All right. So this circle is the circle with the equation r equals root 3 from 0 to 2 pi. Okay, back in section 15.5, you hadn't learned triple integrals yet. So this had to be done with doubles. So yours, you would go, theta goes from 0 to 2 pi, r goes from 0 to root 3, and then you would just have top z minus bottom z, right? So your top z, we got to solve this sphere for z. So we have z squared equals 4z minus r squared. Z squared minus 4z equals, this is really weird. How do I solve, yuck. Oh!
Maybe you complete the square.
Z times z minus 4. That doesn't make any sense. Let's see. How do I solve this for z? This one's easy. That one, I can't figure it out. Oh, I just keep it in terms of, no? Yeah.
It's surface area.
Oh yeah.
Is this surface area?
Yeah.
Oh, I'm doing volume.
That's what I was going to say.
Oh, this whole time. Thank you for telling me. Okay. Oh, gosh, that was going to really, stump me. All right. So then, all right. So we have z squared. I'm going to do this. Minus 4z plus x squared plus y squared equals 0. So it's still weird though. Z sub x, because it's not solved for z.
Right?
Oh, I know what I could do. I could keep the z in it. I think that's okay. Yes.
You need to find it as like the standard circle or like the standard coordinate for sphere. So like the z squared minus 4z, and then you just completing the square, and then you can solve for z without a z in the equation.
Oh. Am I still okay if I just do this?
You wouldn't be okay if I tried that on my way. It didn't work.
And it didn't work? Really? I'm going to have to complete the square to solve for z?
Yeah.
All right.
Wait, are we pretending?
So here we go. Did you convert to ours?
Yeah, I think I did drawing cards later on. But when I'm solved for the... Oh no, wait. Was this when after we learned for?
Yes.
Yeah, I probably converted that. But when I was solving for z, at that point I did.
Let's see. So -2, 4. All right, completed the square. It's been a while. Maybe I should take this off the homework, because this might be. I promise you, there's no completing the square on your test. So.
Say it.
Oh, never mind.
All right. So we're just doing the positive anyway. We don't care about the negative. All right. So here we go. So we get 2 root 4 minus x squared minus y squared times negative 2x. Kill. So negative x, and then z sub y would be negative y over square root of 4 minus x squared minus y squared. All right. So integral of 1 plus x squared over 4 minus x squared minus y squared. I gotta convert this to polar. Plus y squared over 4 minus x squared minus y squared times so if I convert r dr d theta. So we have 1 plus, so this is r squared cosine squared over 4 minus r squared plus r squared sine squared over 4 minus r squared dr d theta. Am I doing something wrong? Because you guys are mumbling over there as though I've messed up. All right. So if you pull out an r squared and a 4 minus r squared, cosine squared plus sine squared is just 1. So you end up with the square root of 1 plus r squared over 4 minus r squared. We did something like this morning again. So you have 4 minus r squared plus r squared, so you end up with just the square root of 4 over 4 minus r squared.
Okay, there's a huge flex.
Okay, which is 2 over the square root of 4 minus r squared. Oh, there's an r. Okay.
Thank Lord.
Yeah, because now it's just a u sub.
Quick question.
Yeah.
So on the test, when they're like shapes like that, will you be giving them to us or?
Yes, I would give you the shape. Honestly, guys, we will. I mean, it's not a terrible integral. It's doable, but I will tell you there is nothing in the world where I would ask you to complete the square to find your z. It's just too much. So I think I'm going to take this one off. If you've already done it, that's awesome. But let's take this off because it's just, I think this part, it's just too much to ask. So, all right.
I don't know if I messed up like when I was solving, but I don't
All right. This is surface area. So thank you for telling me surface area. The part of the cylinder y squared plus z squared equals 9 that lies above the rectangle with those vertices, right? So this is like just a straightforward. You have 0, 0, you have 5, 0, you have 0, 2, and you have 5, 2. So you got this lovely rectangle like that. And we want, if we solve this for z squared equals 9 minus y squared. So z equals plus or minus the square root of 9 minus y squared. So I would just do this in rectangular. So we're doing, it doesn't matter if you go dy dx or dx dy. So my x's go from 0 to 5. My y's go from 0 to 2. I have the square root of 1 plus. So my z sub x is just 0. And my z sub y, so I have, okay, 2 root 9 minus y squared negative 2y.
What?
Is that okay?
Now we're looking at.
Okay. So I end up with y squared over 9 minus y squared dy dx. Is that what you got? Yay. So if I find an LCD, I get 9 minus y squared plus y squared. So I end up with just 9 on top over 9 minus y squared on the bottom. Ooh. So you have a problem here. This is a function you know. So you know that the antiderivative of 1 over root 9 minus y squared is? It's arc sine!
That's where I give up. No. That's where
So, all right, so the 3 just gets multiplied. All right, arc sine, there's no 1 over a in front, so it's arc sine y over a, which is the square root of 9, evaluated from 0 to 2. Yes?
No, like the arc sine, the whole thing for test.
I didn't put it
Thank
in. But I'm not taking this one off the homework. Okay. So, anyway, so you have 3 arc sine 2/3 minus, just so you know, the arc sine of 0 is 0. It's the angle whose sine is 0, right? Okay. All right. dx. So you end up with 3 arc sine 2/3 times x from 0 to 5. So you end up with 15 arc sine. Oh wait, yeah, 2/3. That's what I got. Is that what you the answer?
Yeah.
Okay. So, so y equals x squared looks like that, and then z equals 1 minus y comes down and intersects this at a line. That's supposed to be straight, at a line. So how do we figure out the line? So if I replace my, let's see, how can I solve for where? Oh, z is 0. So you get y equals 1, because z equals 0, right? Okay. So this is the line y equals 1. This is the graph y equals x squared. So if we were to, we're finding volume and they want triple integrals, and this was with no polar, right? So your z will go from 0 to the plane. So your z is going from 0 to the plane 1 minus y. Your y's, just doing a top minus bottom. Remember, this is our region. So your y's are going to go from x squared to 1, because you go low to high. So that's why I always shade my region, right? So I don't like accidentally go 0 to x squared. So my y's are going from x squared to 1, and then my x's would be negative 1 to 1. Does that make sense?
Yes.
Okay. Aubrey, did that help?
Yeah,
Is that what you got?
I always just, the limits are always hard, and I don't know why. That was really easy to do it, but I don't know.
Yeah. Everything's easy once you've done it a bunch of times, right?
So like for triple integrals, there isn't like the way that we're supposed to have it's just like r or like some like 1 or something, right? It's not like
Okay, when you're finding volume with triple integrals, the integrand will be 1. Unless you're in cylindrical, then the integrand is r.
okay, yeah.
All right? Or tomorrow spherical, then the integrand's going to be something totally different.
Thank you.
All right, guys, we'll do more of this tomorrow.
I don't remember.
You're welcome.
Is that one resource area?